Today we'll look at three existence theorems, and they are called that because they guarantee the existence of a certain characteristic of a function. So let's start by looking at the intermediate value theorem. And what if we only know 2 points on a graph of a function? And now we answer this question. Must the function have a value of 0 on the interval from a to b? Does the graph have to cross the x-axis? Well, we could have a graph that maybe there's an asymptote here and the graph jumps over the x-axis. So we would say that the answer to that would be no, it doesn't have to have a value of 0. But then if we said if f of x is continuous, so back up here. Must f have a value on the interval? No, it doesn't have to have a value. It could have a value of 0. But here, if f is continuous, must f have a value of 0 on the interval a to b? And if it's continuous, that means we can't, as we're drawing the graph, we can't lift the pen. So if we're going to trace this, however it's going to go, as long as it's continuous, somewhere it's going to cross the x-axis and have a value, a y value of 0. And this is not only used to find x-intercepts, we could also have a graph like this. F of a is the y value. F of b is the y value of b. And then we'll just say that's 5. And we can ask the question, if f of x is continuous, and this is using a little more of the vocabulary and symbols common for this type of question. So we know we're starting at this point and we're ending at that point. If the graph is continuous, do we have to cross a value of 5? Do we have to have a value of 5 at some point? And yes, we do, because it's continuous. This symbol means is an element of. So must there be some C that is an element of a, b, meaning there's a c value on between a and b, such that when we plug c into the function, the value will be 5. There will be a y value of 5. And so we would say yes, there is such a c because f is continuous. So that's the mean value, intermediate value theorem. If f of x is continuous, then there is c, which is an element of the interval ab, such that f of c is between f of a and f of b. And that's just saying the same concept we just talked about, that here in this example they're saying must there be a value of 5? Yes, there must be a value of 5 because 5 is between the two y values. There must be some x value between a and b that has a y value of 5. Does f of x have an x-intercept, or does it have a y value of 0? And so we'll look to use the intermediate value theorem. It only has one condition, that f of x is continuous. So that's given. It's continuous. So then we have f. Let's look up here, and we're looking for a sign change in the y value. So if the graph goes from 10 to 8, we don't have to cross 0. 8 to 2, we don't have to cross 0. 2 to negative 1, f of 0, f of 0 equals 2, f of 1 equals negative 1. So between these two y values, there's going to be a 0. So that means there's an x-intercept between these. And we're looking over here from negative 4 to 6. We also cross 0. So f of 2 is negative 4, and f of 3 is 6. So we must cross 0 between those two y values. So we're looking for because f is continuous, and because this is true, we can say that by intermediate value theorem, there is a c on the interval from 0 to 1, and we'll just say d on the interval from 2 to 3, such that f of c equals 0 and f of d equals 0. Alright, pause the video and try that one. Remember that we need to say whether it's continuous, so there's a reason why this is continuous. Pause the video, and condition. This is the condition. It's the if part of the statement. The condition is f of x is continuous. So the question didn't tell us that it's continuous, but every polynomial is continuous. And then we're going to check f of negative 1 and f of 1. F of negative 1 is negative 95. F of 1 is 69. So if we start at negative 95 and we go to positive 69, do we have to cross the y value of 1? And so we'll say yes, 1 is between these two values. So therefore, we say by the intermediate value theorem, there is C on the interval from negative 1 to 1 such that f of 1 equals 1. No, f of C equals 1. Okay, let's look at another theorem. Alright, two functions, f of x and g of x. And we say that f of x is smooth we can also say it's differentiable. We are able to take the derivative. We are able to differentiate the function because there's no corners on the graph. But at this point, it's not smooth and it's not differentiable. So let's ask some questions about f and g. Is there an x value between a and b such that the slope of the function is 0? And over here, is there an x value between a and b such that g prime equals 0? So here, maybe right about there, there is a point that has a slope of 0. And here, there's a slope of, looks like it could be a slope of 1, and then it jumps to -1. There's no point on the graph that has a slope of 0. All right, so we're going to talk about a theorem that guarantees the existence of a 0 slope. We need to think about what conditions are required to guarantee the existence of a 0 slope. So now let's think about this. We have a and b. The function's going off this way, it's going off that way, and we need to think, here's this function, what must occur for it to have a 0 slope? So now we think, what are all the possible ways that this point could be connected to that point? And if we connected it like this, we know that there wouldn't be a 0 slope between a and b. So, but if we connected it like that, and it's smooth, we could say there's a 0 slope there, and probably even a 0 slope right there. And we can say that there must be a slope of 0. Because we have f of a and f of b are equal, and it's smooth. Let's look at some cases where there is not a slope of 0. If we have these 2 points, and we have to, and we just draw any graph, what if the graph looked like that? And we say there's a positive slope, but there's no slope of 0, and that's because the graph is not continuous. Or if we just have this point and that point, we just connect them. There's no slope of 0. So what we need to have, there's 3 things required. We have to have a continuous graph. It has to be smooth, and the y values have to be the same. This doesn't work because we could just go straight up. It never has to curve down. So we need to have a continuous graph with equal y values, and it has to be differentiable. If we have equal y values at the endpoints, it's smooth and continuous, there must be a slope of 0 somewhere on the interval. And that's called Rolle's theorem. Continuous on AB, differentiable Alright, so this has 3 conditions: continuous, differentiable, and the y values are equal. If all of these are true, it guarantees, the theorem guarantees, that there will be a slope of 0 between A and B. And we've seen how valuable it is to know that there's a slope of 0, because that's how we find relative extrema. So that's Rolle's theorem. Okay, our last theorem, the mean value theorem. And it's just a generalization of Rolle's theorem. Rolle's theorem is a specific case of the mean value theorem. And now we don't need to have the y values being equal. We have a function going like this. And the mean value theorem is going to guarantee the existence of a slope. So let's just look at, and we'll say the function has to be continuous and differentiable. So let's just think of that dotted line connecting, a straight line connecting those 2 points. No matter how this point gets connected to that point, as long as it's smooth and continuous, it could go that way, it could go that way, they're both smooth and continuous, there will always be an x value between A and B such that the slope at that x value will have the same slope as this dotted line. So this dotted line is the secant line between these 2 points, and then we have tangent lines parallel to that secant line. So this has a couple of them, one right there and then one right there. That's what the mean value theorem is guaranteeing. It's guaranteeing the existence of a value c where f prime of c is equal to the slope of this dotted line. And if we look at the notation for that, this y value is f of a, this y value is f of b. When we talk about the slope of a straight line, we use y2 minus y1, x2 minus x1. But with this notation, we're going to say f of b minus f of a over b minus a. This is the slope of the dotted line, And the mean value theorem is saying that the slope of the dotted line, the slope of the secant line, is equal to the slope of the tangent line. So this is what the mean value theorem guarantees. It guarantees a c such that the derivative at c is equal to this slope of the secant line. And that's the mean value theorem. It's guaranteeing the existence of an x value where the derivative at the x value is equal to the slope of the secant line. Let's just review secant and tangent. So if we have a graph and 2 points on the graph, the secant line is the straight line between the 2 points, and the tangent line is this has infinite tangent lines, but the tangent line at that point looks like this tangent line is parallel to the secant line, and that's what the existence of this value, this x value, is what the mean value theorem guarantees. Okay, mean value theorem. So let's look at conditions for the mean value theorem. It has to be, the function has to be continuous, and polynomials are always continuous, and we also have to have the function is differentiable or smooth. We can say smooth or differentiable, and polynomials are always smooth and differentiable. So the conditions are met. Because it meets the conditions, there must be some value c such that so we have conditions. These conditions imply that f prime of c is equal to f of 2 minus f of 0 over 2 minus 0. Slope of the secant line is equal to the slope of the tangent line for some value of c. Let's find f prime. F prime is 2x plus 1. So now this is going to be 2c plus 1 is equal to f of 2. If we put a 2 here, that's 4 plus 2 is 6. Put a 0, 0. F of 0 is 0. 2 minus 0. So we have 6 over 2, and that equals 3. And we have 2c plus 1 equals 3. 2c equals 2. C equals 1. And we've answered the question. This is the x value guaranteed by the mean value theorem. And let's look at the graph. X squared plus x, x times x plus 1. X equals 0. There's a y, x-intercept at 0 and at negative 1. At 1, we're going to go to 2. I'm just doing a quick sketch of the graph. And we're saying that between 0 and then at 2 will be at 6, 2, 3, 4, 5, 6. Between 0 and 2 we have a secant line. And this is saying that the tangent line at 1 is parallel to the secant line between 0 and 2. Alright, same question. Try it with this function on that interval. Pause the video. And let's think about the conditions. Continuous. Is the polynomial continuous? Yes. Is it differentiable? Yes. And the polynomial is differentiable. All polynomials are continuous and differentiable. Therefore, the mean value theorem applies, and we're going to find the x value guaranteed by the mean value theorem. The implication is that there is a c such that f prime of c is the same as the slope of the secant line. F prime is x minus 1. So we're going to say f prime of c is c minus 1. F of b is going to be f of 1 minus f of 0, 1 minus 0. So we're putting 1 into the function. That'll be a 1/2 minus 1 is negative 1/2. And f of 0 is 0. So we get, this is, no, let's not do that. We're going to do c minus 1 equals negative 1/2. Add 1, and we get 1/2. This says that at an x value of 1/2, the slope of the function is equal to the slope of the secant line. Does Rolle's theorem apply? So let's consider the conditions for Rolle's theorem. We have to have f is continuous, and we know that sine of x is continuous. Differentiable, smooth, and we know that the graph of sine is smooth. F of 0 is equal to f of pi over 2. Sine of 0 is 0. Sine of pi over 2 is 1. So we say that's not, that condition is not met, and we would say Rolle's theorem does not apply. If this were true, then remember that Rolle's theorem would just say there exists a horizontal tangent line on this interval. There exists a slope of 0 on that interval, but we just say there could be a slope of 0, but it's not guaranteed by Rolle's theorem. All right, so same question. Does Rolle's theorem apply for this function on that interval? And go ahead and pause the video and try that. So let's look at the conditions. F of x is continuous. F of x is differentiable. F of -1 is equal to f of 1. All right, so let's think about the graph. And if we put 1 here, we get a value of 1. And if we put a -1 here, we also get a value of 1. So it's looking like Rolle's theorem could apply. But if you substitute a 0, it's undefined. And it turns out there's a vertical asymptote. And the graph is going like this. So we'd say that it's not continuous and it's not differentiable on the interval. So Rolle's theorem does not apply. If the function were continuous and differentiable and the y values were equal, then we would just say there must be a slope of 0 on the interval. And we'll stop there.